Hey students, what's up? Welcome to Science Day 2022. I hope you're having a good time and learning a lot of fun things. Today, I think we're going to have a pretty fun video here. We're going to look at some cool stuff involving music and sound, and we're going to do that by examining waves. Now, there are all sorts of waves all around us in the world. If you go to the beach, you're going to see some waves. If you're looking at any color, that's just a light wave. And if you go to a sports game, you can even see some waves there. And today we're going to be talking about sound waves. Now, a sound wave is how sound travels from one source to somewhere else. As we all know, if someone stands 10 feet away from you and they talk to you, you can still hear them even though they're far away. That's because when they talk, their voice vibrates the air in front of them, it travels to your ear through a wave, and you hear it. This is how all sound works in the universe. If something makes a noise, it is vibrating the air or even a liquid or solid around it. Those vibrations pass through that medium or just physical object, and if there's something listening on the other end, they can pick up on those vibrations and hear a sound, whether it's an ear or a microphone or something like that. Now, as with pretty much everything else in the world, this whole idea is all based around math. And I know math might sound scary and it might be a little intimidating, but the more you learn about it and understand it, the more rewarding it is, and you can find actual connections with things you see in the world, and it can be really cool to learn something and then see it in practice. And we're going to go ahead and start this today by looking at a sine function. Again, bear with me, don't be intimidated. I know when I was in high school, I didn't really understand what a sine function was, partially because you're first introduced to it by your probably trigonometry teacher telling you, push this button on the calculator. You think it says sin, but your teacher calls it sine. You do some stuff with calculators and triangles, and you don't really know what this is, but I'm going to show you a graph of it that maybe you've seen by now. So this is the graph of a sine function, and I think it's really helpful in understanding what a sine function is. Because when you look at it, you can see, oh, it's a wave. It goes up and down smoothly, and as time goes on, it just continues to go up and down between two values. And if you want to graph something that goes back and forth repeatedly, like a swinging pendulum or a day and night cycle, you can graph it with a sine function and it's going to work great. And as you get further along in your math education, you might see diagrams such as this that show you altered sine functions where maybe it's stretched out or move up or down, has different properties, and you learn about things like amplitude and phase shift and frequency. And the cool thing is, if you're interested in music or sound or audio engineering, these ideas are super important, and they have real straightforward connections to what you're doing and how sound works. So for example, in the middle of this graph here, we have the amplitude, and that's going to determine how loud the sound is. So a higher amplitude is going to be a louder sound. And the frequency of the wave is how many of these crests and valleys we see. So if we saw a lot more of these little shapes squished into this picture, it would have a higher frequency, and that would lead to a higher pitch. And that's kind of intuitive because we hear a high frequency and we think of like a high whine or buzz sound already. And then this is a sine wave. It's really smooth and nice. Not all sounds in the real world are going to look like that. If you look at the sound wave, something such as a human voice or a car engine is going to have a much crazier looking wave. You're not really going to see a sound wave look like a sine wave unless it's something really clear and sustained like a bell or a single musical note. Most waves are a lot more complicated. So I know I said that this was going to be a really cool and exciting video and then showed you a bunch of math, But now we're going to start connecting that, and I think it's going to be a lot of fun. I pulled up my digital audio workstation called Logic, and I have here probably the simplest instrument in this whole program. It's hardly even an instrument. As you can see here, it's called Test Oscillator, and that name kind of implies that it's more for testing your system or your speakers than any musical purpose, but it's fun, and I chose it because you can see that it has a sine wave mode. There's even a picture of a sine wave, and it's just a simple, straightforward tool. I have the frequency set to 440 Hertz, which is just like a standard A note, and then over here you have a volume control. Now, I recorded a little sample of me playing this test oscillator, and I'm going to play it back. We're going to listen to it and then look at the sound waves for it. Oh. Okay, so as you could probably hear, it was a smooth, simple tone, and then it got louder. So what I have here is the actual sound wave. I turned the file into something we could look at, and if we zoom in, look at that. That's the actual sound, and it is a perfect sine wave like we were looking at on the graph. It's just up and down, really smooth. The reason there's two is because it's a stereo track, so there's a left and right. But that's a sine wave, and I'm zooming in and out. That's why it's moving around. But check this out. Like we said earlier, it started out quiet, and then it got loud. If I go over to the right more, when it starts to get louder, you can see that the amplitude of these waves is getting bigger. They are larger and larger, and then they get really big here that they're actually clipping a little bit, and that's why it was sounding sort of distorted because it was too loud. But these are a lot bigger than the waves we saw earlier, and that's because it was a louder sound with a higher amplitude. So now we're going to look at another example. This time we're going to look at the frequency and how we can see that. So again, frequency is just pitch and how high or low the tone is. So I'm going to play a sample here. It's going to be 4 tones, each getting higher. You can see here that I have 4 kind of dots, and each time it gets to one of these dots, that's me playing another note, and you'll see it gets higher. Last one was kind of painful. So now we're going to go to each one of these little dots, each one of these different notes, and I'm going to zoom in all the way and look at the wave shape, and they're going to be a little different. We're going to see higher frequencies in them. So I'm at the first one here. I'm going to zoom in all the way, and you can see we can't even see a whole wave. We see maybe half of one goes from bottom to top, and that's it. And now I'm going to go to this second note here, and we're going to zoom in all the way and say, okay, we see it goes about from the top down to the bottom, back up to the top. We're seeing almost, well, that is pretty much a whole wave there. Now I'm going to go to the next note, this one right here. We're going to zoom in all the way. And okay, we see a pattern repeating. We see top to bottom to top to bottom. And now we're going to go to the final note and zoom in all the way. And we're seeing a lot more than the first one. The higher frequency, the more we see these waves, the crests and valleys appear. So yeah, like we said earlier, higher frequency means the waves are going to be more tightly packed together instead of long and stretched out. We've seen now that that's true, and that's how sound works. Now I'm going to show another fun idea. This is the idea of phase and how waves interact with each other. So I have this green sound here and the red sound here. They are both a sine wave at the exact same frequency, at the exact same volume, synced up perfectly, and when I play them, you're going to see something interesting happen. We don't hear any sound. You can see on the left that the volume was playing, the volume was up, so it was outputting noise, but we didn't hear anything. And that's because if we zoom in and look at the sine waves, you can see that they are the exact opposites. So when the green one goes down, the red one goes up. And when the green one goes up, the red one goes down. So if you have two sounds that are out of phase like this, they will cancel each other out and make each other quieter. Now, they won't always completely cancel out, because in the real world, two sounds aren't going to be exactly out of phase, but in this sine wave, really clean and precise workshop in the program, we can totally cancel that out and you won't hear anything. But when you're recording instruments, this is still something to keep in mind and really important to make sure that all your recordings are in phase and they don't cancel each other out, because you want to build strong sounds that work together. The best example where this would be important would be a drum set, because drum sets are one of the trickier instruments to record. There's a lot of different drums and you usually use a couple microphones on them, and if you don't do it right, the microphones can work against each other rather than with each other, and this will really affect your bass drum sound, because the bass drum is the largest drum, it has the lowest sound, and those bigger waves like we saw earlier, the lower frequency large waves, they're a lot more prone to canceling each other out with phase issues. So if you don't set your microphones up right, when you record, they could cancel each other out rather than making each other stronger and louder and giving that nice punchy sound that you want to go for. So now I'm going to demonstrate how you can set your microphones up to record these things in unison together, and then we'll look in the software and see that it actually works. So one important idea is that sound, while it travels very fast, doesn't travel instantaneously. So if a microphone is 2 feet away from a sound source and another one is 5 feet away from a sound source, they're not going to get the sound at the same time in the same way. So if you want two microphones to be in phase with each other in terms of the bass drum, you want to make sure that they're both the exact same distance away from the bass drum. So that way, when you play it, they're going to pick up the sound at the same time and they're going to be in unison. And this is actually pretty easy to do. What I'm doing here is getting a cable, holding it on the bass drum, and then stretching it out to one microphone just to get a measurement. And then I take that length and stretch it out to the other microphone and move it around back and forth until they are the same distance apart on the same length of the cable. And once I do that, I know my drums are going to be in phase, and then I can record them and they're going to be strong and in unison and in phase. So now that our microphones are all set up properly, we're going to record a quick sample and then check it out in the software. Okay, so here we have the two recordings of the drums, one from each microphone. One is blue, the other one is red, and it looks like they're perfectly in sync, but remember the phase issues that we were looking at earlier, those are really, really small, so even if they're perfectly in sync like this, when we zoom in, we could just see that one goes up and the other one goes down, and we don't want that. We want them to both go up and down at the same time, so that way they are building a stronger sound rather than canceling each other out. So what we can do is zoom in really close and see how these waves behave. And interestingly enough, because we set the microphones up properly, they are both going down at the same time and up at the same time, and it gives us the strong sound that we wanted on the bass drum. and it's really fun because we're using math and physics to be better artists and musicians. And a little bit of understanding about math and science is helping us in other areas that we might not have expected. And I do this all the time when I'm recording, and there's so much other stuff you can do using physics when playing music that it's fun to make those connections and share them with my physics friends and my musician friends. And I recommend anyone that's interested in music to really look at physics of all this stuff. There's a lot of math that you can apply that makes you a better producer and musician and audio engineer. Now, if you want to play around with this, I found this really cool website. It seems to only work on phones, but it's called signalgenerator.sciencemusic.org. And what you do is you touch around on the left side and you can change the frequency and amplitude of a sound wave, and you get to hear it and see it graphed at the same time. And it's really fun to play with. You can hit this complex button and then it makes it sound like R2-D2 or something. But it's a fun way to hear sound and connect it with the sine function that it connects to.
Thank you so much for watching. Please follow us on social media to find more about our upcoming events.